Hello,
Hello.
Crusher.
Hello. That was Elwelly. Hello. 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 Thank you for saying okay. Uh, and good afternoon, Cheska, and and hello, Avani. And um Felix was so embarrassed at me that I didn't hear the sound on that TikTok. I'll see it someday. Of course, I'm embarrassed that I watched a TikTok, but good afternoon. How are you? Good afternoon. Just there she is. Okay. Hello. Good afternoon. And I was about to say, oh, good afternoon, Giselle. Good afternoon, Marilyn. Good afternoon, Matthew. Good afternoon, Yavi. Good. Oh, not to. Wasn't it? Wait, is that a joke? See because I can't see Jessica. I can't. Was it not whatever you? I get them all confused. All the social media things. The thing that you showed was that not? Or is she messing with me? Oh. Okay. Yeah, yours. Yeah. Okay. I think that was the first. Anyway, and there's well. Oh, all right. Do I want? Oh, maybe. Yeah. Oh, wait. But does that mean if I actually follow a link to TikTok, am I gonna like become a different person? I'm not sure, but yeah, or so. Oh, and there's just so people are. Wait, is today the day that everybody shows video? Is that what's? I will say. Nah. Okay. Wait. All right. So we do have to do physics today. Interestingly, in the other class, it was the first day that nobody showed video. So I thought it was that time of year where everybody's just dying, which I am, which we all are. But if this is going to be the class where you guys just like rock the video, that would be amazing. Anyway, all right. It's good to see. It's good to see. Hi, you. It's good to see Michelle F. It's good to see Ivani. It's good to see Giselle. It's good to see El Welly. It's good to see Amanda. It's good to see Michelle Q, sort of in black and white. Okay, I'm going to stop talking about that. We're going to do. Okay, that's the link. Thank you very much. Good afternoon, Melita. Do I wait? Good afternoon, Melita. I don't see you when I see you. Yes. Okay. And good afternoon, Amanda. Okay, we're going to do some physics. There's Melita. All right. That we are going to do physics. Yes. Couple of quick announcements. So I want today I'm going to go. We have one. I know it's an odd schedule. We still have one more class next Monday for good or for bad. For good for me. Where we are going to do final bits of the material, believe it or not. Like we have to just like close down this shop so that you're fully ready for 204. So you will be still learning things in a soft way next Monday. That's number one. So please come. Number two, if you have okay, very quickly. If you have like a couple here or there old assignments that you still want to turn in or something for points, you can until midnight of Monday of next week. Like, don't give me a million, but if you have something here or there that you want to turn in, sure. If you have, if ever you got feedback on something and you wanted to do a revision on anything you got feedback on, which is spotty how much feedback you got, but you can do that by Monday midnight. Um, if you ever got something that, and if you whatever, I don't need to over explain this. I'm saying you could still tie up loose ends by Monday night. Don't if you've never done homework to this point, don't give me like 10 assignments on Monday. Like that would not it would not serve any purpose. I'm sure you get that. Right today, as soon as I get rolling, I'm going to finish going over your very last homework 9, which again, like still, if you want to do something with that, you can, but I'm going to finish going over homework 9 right now in today's class. Then let me make this clear. Wait, is there someone in the chat? Okay, let me make this clear. This is like this is an apology, a recognition, and announcement, adjustment. Like, so I know, and you know that many of you still have never gotten feedback or score back on your midterm. I know that, and you know that, and that's totally on me. That is my bad, and that is not cool. And I apologize. And well, of course, we still have to have a final. You still will. Your work on that still will be credited, and it still will count. It's just that I know it puts you in a really bad spot because you can't use that information to help you with your final. I understand that, and I've committed this mistake before in the past, and this is what I do. You are going to take a final because, like, you are going to take one, But what's going to happen is for each of you, you're going to take the final. It will be shorter than the midterm. It will hopefully be less stressful than the midterm either way, no matter what. But then whichever, and everything will get scored in time for you to get a final grade. But whichever one you do better on will count more for you, for each of you. Like not so. For any individual of you, if you did if it ends up that you really did well on the midterm and you didn't even, but you just never knew it, and so then you don't even need to worry. Then the final won't count as much. If you did really well in the midterm, it'll count twice as much as the final, and the final won't mess up your grade. But if it turned out that you didn't do really well in the midterm, but you didn't know that in time to do anything about it or whatever. Then, or if you're back in your mind, you've been worried that you didn't do well on the midterm, but you don't know, or this or that, just rock the final. The final will be the opportunity to rectify that situation. So if you do better on the final, it'll count twice as much as the midterm. Whichever one you do better on will count essentially twice as much as the other one. And that's not a trick. Again, we're going to do everything within reason that I can do, everything within my system that I can do to give you the benefit of the doubt in every way is what we do. Okay, like we can't make up grades that don't exist. We can't pass people that never did any work or blah, blah, blah. We can't give the physics, we can't do the physics exams for you. But in the end of the day, trust that the final grade for you in this class will be far more determined by whatever your best days were and your best work was, not your middle and not your worst. I hope that makes sense. That's what the grading system is designed to do, to reward you at your best, not at your middle and not at your worst. So, okay, that doesn't mean everybody gets an A, but it means everybody has more of a shot at an A or a B plus than you might be thinking. And it means that I recognize that you should not be punished for my imperfections. I mean, that's the simplest way I can put that. Okay, so there is a final exam, of course, and it'll help you, not hurt you as much as possible on that. And then I'll look in the chat in a second. So today we're going to just finish the material of the homework. We're going to finish this homework assignment. But as you may already know, you have lab right after this period. I gather it's going to be remote today. Okay, I think you got an announcement to that effect. Okay, that is what it is. But you do have lab period after this. You will have noticed that like 5 minutes ago, a practice final exam got posted in your Google Classroom. That's what you're going to be working on in the lab. Like you will get a chance to practice for the final exam today after this period. Stop me if I'm confusing sections, but I don't think I am. And don't run away. Like I don't, whatever Mercedes is going to do with breakout rooms or whatever, that's her business and your business. But it would be very worth your while to use that time to work on the practice, however you guys do, because of course, then she will be a resource there to help with questions that you have or solutions or answers or whatnot. That practice is not exactly what your final exam is going to look like. There will be like some tweaks, but it's a very good indication. Your final exam may be shorter than that. Like I actually hope it will be shorter than that. Maybe there'll be choices involved or something. But you can't know that till you get there. So know everything in the practice and certainly know that your final won't be longer than that. And your final won't have anything involved that isn't involved in that practice. Okay, you get my point, I think. I'll look in the chat in a second. But then the details of when your exam and everything are posted and stuff are now in Google Classroom, but we'll review that again on Monday. The bottom line is it's take home again, just like before. You do it sort of at the beginning of the final exam period or the reading period or whatever. And it's all the same rules apply as before. Hopefully it's less of an experience than the other one. Hopefully it all works out, all that stuff. Wait, what's the last? So on the very last day, we're still going to be covering some last bits of material that you need for 204. So if you see anything in the practice exam, like toward the end, that you don't fully think you recognize, it's probably a short question here or there toward the end. You can assume that's something that we're going to talk about on Monday, and it's not a huge deal. Or if we don't, then it's not on your exam. Okay, okay, wait. Okay. I'm looking at. So I think those are the basic things. But this next lab period that you have with Mercedes, honestly, in some ways, I think will be more important than I think it'll be a more constructive use of your time, really, than like anything I have to say in the next hour and a half, or not really, but you know what I'm saying. Like, I would take that seriously. It'll save you a lot of heartache in the upcoming week. Okay. Okay, I'm looking. So I'm gonna turn back to the homework in a second, but I'm looking in the chat. Okay, good afternoon, good afternoon. Oh, thank you for saying so, Giselle. Okay, I appreciate. I mean, I think I know what you're talking about, Giselle, and thank you for your understanding. Okay, Avani's question. Okay, man. And yeah, if Amanda answered Avani's question by looking in whatever it says in the Google Classroom, I think is right. I'm finding finals period very confusing this year because of the fact that you have these classes on Monday, but then we don't on Tuesday, and then there's like reading period. So I'm like a little confused about everything. So if I made an egregious error somewhere, or if all a bunch of you think that the dates that I put in the Google Classroom like really don't make sense or really conflict with Orgo or something like that, you can let me know. But you know, after the period with Mercedes, if sort of you all come to some conclusion that I've vastly misunderstood the situation, you can reach out to me. But yeah, whatever it says in Google Classroom is like, I think right. And I'm going to assume that Amanda, yeah, whatever Amanda just said. And I'm going to assume that, like, since her head didn't blow off while she wrote it, nor Ivani's head didn't blow off while she wrote it, I'm assuming it's okay, sort of. But like, yeah, okay. The idea is you should have like 4 nights or so at home to do it. Okay. Oh no, now Chris is here. Okay, now Chris is here. Everything I just said wasn't true. No, okay. All right. Since there are so many of you on video, which can you just like raise your, is everything I'm saying basically on page with what you think about okay, thank you, Ivani. Okay, thank you. Chris, you just walked in. How could you know what I just said? Well, okay, all right, fine. Now we know where his stock response. Okay, so I'm going back. Now what I'm going to do is finish this last homework assignment, which I think you can see on the board. Yes. Okay, so it's homework 9. So we had this big boulder that's rolling down the hill. And I believe I'm up to question D. Again, stop. I'm just going to my goal is to finish this homework assignment, at least with answers, by the end of today. And it worked in the other class, so it should work in yours. So that's why I'm talking fast, but it's all in the PDF, even if I don't get to it. So you should, from here on in, we're just finishing this last homework. So definitely do put things in the chat if you have final concerns about any of this. But okay. All right, so part D of question 1 of the boulder going down, it asks, what is the net work being done?
Can I ask you a question?
So yes,
sorry,
please.
did we do part C? Is it possible that we skip part C?
Oh, it's very possible. Sorry. Yes. Okay, hold on. Thank you. It's very possible. Let me look. And at worst, what I might do is just say it. I might say the answer right now so I don't mess up the PDF. But yeah, part C.
You did skip part C from last class.
Oh, sorry. I totally did. Actually, thank you, Melita, and thank you, Chris. Okay, because that is actually super important. Okay. I'm going to say it. I'm not going to, well, all right, here. Yeah. Okay. Thank you. The answer to C is important. So question C was, what is the work done by the normal force from the ramp as the boulder rolls down? Okay, that's the question, everybody. Thank you, Melita and Chris, like seriously. The question is, what is the work done by the normal force on the boulder? And the answer is 0. 0 joules. Okay, that is the answer. But let me be very clear. But it is not a trick question, and it's also not it's not a silly question. Like, if we drew a free body diagram, which I believe we did 2 days ago, the normal force is in the free body diagram. Like, the normal force is there. It is acting. The ramp is exerting a normal force on the boulder, and the normal force has all kinds of important consequences throughout the problem. Like, it's doing things. It's just that the one thing that force is not doing is work. And the reason it's not doing work, right? Like, strictly speaking, remember, work by definition equals the path integral of force, right? But in all these cases, so I'm doing this quickly, in all of these particular problems of this homework, the F comes out of the integral because in these problems, F is constant, right? So F comes out of the integral. So then we end up not having to do calculus in these problems. We get that work in this homework, right? We get that work is the dot product of force with displacement. But dot product means the force magnitude times the displacement magnitude times the cosine of the angle between the force and the displacement. And always, and the key point here, and this is going to come up a lot in this, like in the rest of this lecture today, but like the key point here is that the angle between the force, the normal force, and the displacement, which is along the plane, they are at right angles with each other. The angle between them is 90 degrees. The cosine is therefore 0. So mathematically, the work done by the normal force is 0. Couple of things about that. So it's like one takeaway is it's very important to understand that any force that is acting perpendicular to a displacement is there. It's important, but it's not doing work. To do work, you have to have some kind of parallel component. Okay, fully perpendicular means no parallel, but the more parallel you are to the displacement, the more work you're doing. But if you're perpendicular, you're not parallel at all. Okay, so the normal force is not doing work on the ball. Someone asked in the other class, can this be a takeaway? Like, can you always believe that the normal force from a surface is always doing 0 work on something sliding along that surface? Yes, you can. The normal force by definition is always perpendicular to the surface. So anything going along the surface is necessarily being displaced perpendicular to the normal force. So yes, you can take it to the bank that normal forces don't do work, at least not along. In the context like this, normal forces don't do work. They do something, which we're going to get at by the end here, but they don't do work. And what do I really mean when I say they don't do work? I mean they don't transfer energy. The normal force is not transferring kinetic energy to or from the boulder, i.e., the normal force is not giving or taking away any speed to the boulder. Okay, so the answer is 0. And I'm glad and I hope that's clear. So the answer to part C was that the work done by the normal force is 0. And is there anything else in the chat? And then the one other thing, I'll say this quickly because it keeps coming. Do I want to say this? 2 things I'm going to say quickly. Like I made you sit through like 2 days of talking about calculus. And then it looks like once again, we're not really using it. I have to admit that is true, but let me be very clear about that. I spent 2 days setting up the calculus for the definition of work because the definition of work really does involve calculus. And that is for the purpose that anytime we ever have a force that changes from position to position, then in order to calculate the work, we really do need an integral, and we need to understand the integral and do the calculus. Now, to be super honest, the reason I'm making such a big deal about that is the very first thing that happens in physics 204 is the very first thing is we deal with a force that changes from position to position. Like it's called a spring force, okay? Like as soon as we hit the ground running, like whoever your instructor is in 204, like you're gonna have to deal with springs. You're gonna have to deal with that integral like right away. So that's why like it's in your consciousness, hopefully right now, and you're letting it sink in. But that's on the one hand. On the other hand, yes, every exercise on this homework sheet, on our last homework sheet, happens to be a case where the force doesn't change from position to position. So here, what we're really emphasizing is these other aspects of work, the whole angle aspect of it, okay? I'm not trying to confuse you. We're trying to do things in pieces. So work is an integral. It is an integral of force. But as long as the force is constant, force comes out of the integral. So then it's just force dotted with displacement. That is the case for the rest of this sheet, that we're just worried about force dotted with displacement, like no infinitesimal displacements to deal with, just big old displacement. But the thing that we're focusing on here is this whole dot business of the angle. And so the last thing I'm going to say about that, the last thing I'm going to say right at this moment and then go on is the definition of work is force magnitude times is the component of force parallel to displacement multiplied by displacement, right? Like however you say it, whether you say it with cosines or you say it with dot product or however you say it, what we're trying to say always is we only care about the components of force and displacement that are parallel with each other when we're calculating work, however you get them. Okay, so why I'm saying that is often we write that as F times X times cosine of theta. Whenever we write that the dot product is F times X times the cosine of theta, the theta we mean when we say that is the theta between the force and the displacement. That may or may not be the theta that's given in some problem. It may or may not be related to the theta that's given in some problem. Like, just to be super explicit, and that confuses people a lot. Like, maybe next semester I won't use theta, I'll use some other, Greek letter. But like here, for example, the angle that's given in the problem of 33 degrees, that angle is the angle between the plane and the horizontal, like, tabletop or like lab floor or lab table, whatever. Like, that 33 degrees is the angle of inclination of the plane. That's an angle that means something to some parts of the problem. But what we're asking right here, when we ask what the normal force is doing, we're asking the angle between the normal force and the plane itself. That is not 33 degrees. That is 90 degrees. I'm not yet. None of you like said anything. I'm not yelling at any of you. Like, no one made a mistake about this, like, right in front. But this seems to be a common misconception that's like coming up in the two classes. So I'm just trying to clarify. Whenever I say F X cosine theta, I don't mean just any theta that was given in the problem. I mean the theta between the F and the X. Okay, I'm going to go on. But all right. But I'm glad that. See, you ask a question, I get all hot-headed, for heaven's sake. Where's Felix? Okay, no, so the answer to C, thank you, was 0 joules. Okay, so that's C. So now I'm going to go on to D. D asks, what's the net work being done on the boulder? That means what's the sum of all of the works being done on the boulder? That means take the work done by every individual force and add up all those works, accounting for negative signs. Or conversely, it means add up all the forces, accounting for negative signs, get the net force, and ask what the work is being done by that net force. So I'll do it the first way. Something got erased here. The net work equals work plus work. In this case, in this case of the boulder, we have gravity doing work on it, but we also, we calculated in earlier parts of the problem that gravity was doing positive work, but friction was doing negative work. So I'm adding the two works together. It's just that one of them happens to be a negative, right? So I'm adding all the things doing work. Like the normal force, we just established is doing nothing. So it's not contributing anything to this sum. So it's the work done by gravity plus the negative work done by friction. Notice there too, and then I plugged in the numbers, as you can see. But notice, like, in some ways, I'm just like lifting the numbers and the results that we got from parts A and B in the homework. But do notice the work done by gravity is mgh, the positive, because the thing is because the boulder is rolling in the direction that gravity is pulling. So gravity is succeeding. It's doing positive work. It is transferring kinetic energy to the boulder. Friction's going the other way. It's negative. But notice that the positive work done by gravity is force of gravity times it's force of gravity times component of displacement that's parallel to the force of gravity, right? I mean, the boulder is displacing this way. But all of my yammering Monday was meant to establish that if the boulder's going this way, while gravity's pulling this way, so only the component of this that matches, that's parallel to that, matters with regard to the work done by gravity. So the work done by gravity is mg times h, and it always is from now on. The work done by gravity is either positive or negative mgh. But the work done by friction is F times X, right? Because F is acting in the direction of X. We don't have to take any components of friction to, like, strictly speaking, it's F times X times cosine of the angle between them. And the angle between them, between friction and X, strictly speaking, is 180 degrees. I mean, right? Like they're on the same axis, but they're pointing in opposite directions. So that's where the negative sign came from. But it's like the cosine of 180 degrees is -1. All right, I'm dragging this out for a small change in pace. So the work's done, the net work done is mgh minus f of x. So I plugged in the numbers we got the other day, and we get that the net work done on that boulder is 7,936 joules. Really, I should say, like, really it would be better if I said like 7.94 times 10 to the third joules. I would be a better person and I would go to heaven immediately if I actually used scientific notation. That's actually a thing. Like, you go to heaven immediately if you use scientific notation. It says it in Deuteronomy. Okay. I shouldn't make jokes like that. Okay, so that's that. Okay, so if there's no questions on that, I'm going on to the next one. So the network is like 8,000 joules. Now, why do I care? Because so Michelle F. She's like, you're right. You are. Michelle F. is so crazy, yo. Okay, wow, you guys are really listening to. It's funny how you like listen. I have to really be careful about you guys. But the converse does not. By the way, the converse does not obtain. That is, I'll stand by this. Yes, you go to heaven. Like, I mean, of course, that kind of sounds like it makes sound like you die immediately. But anyway, but it does not mean that if you don't use scientific notation, then you go to the other place. I'm not saying that, because it doesn't work that way. See, because you think you go to a college of criminal justice, but actually in physics, you go to a college of criminal mercy. Contemplate on that and get back to me. Okay. All right, so E, assuming the top of the ramp. Okay, so now they give you the speed at the top of the ramp. They give you the speed, like, who cares? Why? Because they're going to ask you about the speed at the bottom of the ramp. Now, the whole thing, okay, the whole thing now is that we're going to use this work kinetic energy theorem. We're going to say work is the transfer of energy now. And the emphasis here, the thing I'm trying to emphasize is work is the transfer of energy. By doing network is the transfer of energy. The network done on the boulder will raise the boulder's energy by a certain amount. So in other words, if we want to know how fast the thing is, and kinetic energy ultimately indicates speed. So if we want to know the speed at the bottom of this thing, knowing the work done, that won't by itself tell us that. The work done will tell us ultimately how much speed we're gaining. So if we want to know the final speed, we got to know the initial speed. Okay, I think that's clear. So they give you the initial speed of 2. They say, so I say the net work done on the object is the change in kinetic energy. So that's the change from some old 1F mv squared to some new 1F mv squared, right? So I plug in the numbers and I get that the final speed must be approximately 13.8 meters per second. Slight sidebar, just notice, this is starting to set up a pattern of like when we care about energy, why we care about energy, when we use energy in work tends to be when you might want to write this down, when you know the speed when you know the speed over here and you need to know the speed over there. If you want a speed to spot correspondence, like you know the speed at a spot in space, but you need to know the speed at a different spot in space. That tends to be when we use work and energy. Like that tends to be when we choose these equations and so forth. If you're looking for like, how do I start problems? And quick thing on that, you might say, well, isn't that always physics? Like, isn't every physics problem like sort of that? No, most of the physics problems good question, but most of the physics problems we were doing up until this point really treated time as the independent variable. We tended to be solving problems where like you knew something like the speed or something at this moment in time, and then you had to figure out the speed at this other moment in time. And we used acceleration and all of that to figure that out, and then forces. Now we've moved our focus to making different positions in space, different spots, the independent variable. So that's like a big sort of clue, like when do you use what in physics? When it's a speed to spot correspondence, like And it could go the other way too. Like maybe you know what spot something has a certain speed. And then someone's asking you, well, where will it be when it achieves this other speed? In fact, that's like literally one of the first homework in Physics 204. If someone ever is like, I know the spot, I know the speed at this spot over here, what's the spot going to be when the speed is some other number? Whenever it's speed spot correspondence, that's when we think about work and energy. Okay. And that's what's happening right here. So, okay, that's like a problem solving pro tip for particularly for next semester. Okay. So next page, problem two. So now it's the same ramp. It's all the same numbers, but now Sisyphus, look it up. Not in Deuteronomy, different book. Sisyphus is now pushing the boulder up the plane. So we want to know now, okay, this is sort of interesting now. So now we got like a lot going on. Okay, we have a lot going on. We've got Sisyphus pushing the boulder. We've got gravity pulling down on the boulder. We've got friction also pushing down on the boulder. Down now because the boulder's going up now, right? So we've got and we've got a normal force still, but we got like 4 forces acting now, and 3 of them are doing work. So there's like a lot going on here. And one thing that the problem is designed to sort of like make you want to it's trying to help you realize is like each one, physics is always, it's like the sum of its parts, right? Like each one of these forces is still doing work, even if that work is not at the end of the day, like the winner or the final effect of what we see. Each one of these forces is doing its own work, and we add them all together to get the network, and the network will, in the end of the day, transfer energy to this boulder. So it's asking us to go individual piece by piece. And the main thing to pay attention to with these answers, like obviously if you can see them already, and if you don't like one of the answers, let me know. But one of the main things to pay attention to is negative signs. Negative signs really do matter with all of this stuff, and perhaps they can be confusing at times. And I think actually, no joke, I think Chris said this on Monday, the thing I'm about to say, which is the whole deal with work is when the force and the displacement are in the same direction, or like the relevant components of force and displacement, where they're in the same direction, then the work is positive. And when they're in opposite directions, the work is negative. That is true. That is, I believe, what Chris said. And it's true no matter what coordinate system you're in, right? A positive times a positive is a positive, but also a negative times a negative is a positive. So no matter what, that's the case. And it really makes sense if you think about work as transfer of energy. It means when I push you and you go that way, I'm doing positive work, I'm speeding you up. And the converse is true. Okay, so question A asks, what's the work done by gravity? Even though the thing is going up, gravity certainly is doing work on it. It's MGH. Like you can take that to the bank. The work done by gravity magnitude is always MGH, but here that work is most definitively negative because the gravity is of course pulling down while the boulder happens to be going up, right? So that means if gravity were the only game in town right now, the thing would be slowing down, but gravity's not the only game in town. So it's just doing negative work of negative MGH, 9,000. I should do science. Oh, I'm not going to heaven. I'm so not. Also, I'm not going to heaven because I mentioned Deuteronomy, but the book we're in the middle of right now is Bereshit. So what? Okay, what am I even talking about? All right. Okay. I don't know. Yes, I do. Okay. When did heaven come up? Interestingly, heaven came up the minute Chris wasn't in the room. I don't know what that said. No, it came up because of scientific notation. Obviously, heaven always comes up because of scientific notation. Duh. Okay, I'm totally sorry. It's the end of the semester. I'm losing my mind, as you can tell. It's Potiphar's wife's fault. Okay. But okay, hopefully. Oh my God, Michelle F. It's like, oh no. And just when I was about to get back. All right. Michelle F. Her timing is perfect too, because I was about to. All right. I'm just going to pretend that Michelle F didn't like graduate from the same asylum that I did, but I'm about to get back to physics, except you know what I'm about to say. I could see the car pulling up. We know, okay, this is all going to fall apart. I'm going to quickly do physics before the Team Rocket comes in. Wait, that's all right. Wait, so the work done by friction, that was also negative, right? So the work done by gravity was 9.350 times. I'm looking at chat, but I'm not. And the work done by friction is negative 1,000. I gotta do that in scientific notation too. 1.41 times 10 to the third joules. Okay, I can't resist. I am looking at chat because we're gonna be interrupted. That's why. I'm gonna find the person who made math. Dude, when you were in your, I'll tell you this, Chris. Okay, good one, Michelle F. Fair enough. But here we go. But Chris, well, I'm gonna postpone my comment to Chris. Hello, good afternoon.
Hello. Just to clarify, I am here to stall.
I'm not laughing.
Yes, you are.
I
Yes,
am.
you are. Yes, you are.
Okay, I am. That is funny.
Felix, he gave us a test.
Wait, what? Felix, what did he say? Felix, don't do that. That's me.
You are not allowed to give tests. Also,
Oh yeah, I'm not allowed to. Also, hi.
no
But
test.
you can see that you
No.
can, okay.
No.
All right.
No.
All right.
No.
I don't get
Bad.
All right.
Bad.
I do not.
Bad.
All right,
Bad.
easy,
Bad.
easy. Okay.
Bad.
Okay. All right. Good talk. I'll see you in a few minutes. Oh my God. All right. Okay. Good to see you. Love you. Okay. I do not give tests, by the way. I merely proctor them. Tests come from the universe, and I'm just a conduit. Okay. And not a very good one, I might add. All right. And by the way, it's I think, yes, the first commandment is like, thou shalt have no other notations before me besides scientific. And I think the second commandment, well, really the fourth, is like, honor thy father and my mother. But that one was definitely missed in my household. Like, that tablet got broken in my house. Okay, we're going to okay, next worked. Okay. Wait. Yeah, see, I shouldn't even. I don't know if it was worse, him or you guys. I mean, I mean, like, thank goodness I use this class as group therapy. Otherwise, I would need therapy right afterwards. Okay, yeah, no, you are daily combo. Always remember. And no, I could tell you that he did not ask his mother that because he knows which parent to go. I mean, he knows what he's doing. No, you are very nice. You are actually very nice. Felix is mini you. That's not nice. All right, sorry. Okay, look, guys, I'm gonna fail your final exam. You are very nice, actually. I don't want to joke about that. And you're very hilarious. And you are very nice and hilarious at keeping me from doing physics. And Michelle F can take a gap year from the asylum, and then she can come back and get a diploma after. Okay. So this next question, thank goodness, I was about to make a big deal of, but this next question is exactly like what we just did, right? It's the same question. What's the work done by the normal force? So here I'm dragging it out. Gab. Sorry, now Melita's oh my God, Melita. Okay, wait. There's definitely an honor thy Melita and thy Melita commandment. I know that. Okay, this thing that's on the board is. Stop, people, stop. Don't you know this is so, don't you know that I don't take medicine, so I can't. Yeah.
I'm sorry.
No,
I'm so sorry.
no, that's a good one, actually. And yes, and actually you figured that out like way earlier than a lot of people. No, good for you. Yes, oh my God. All right. I hope you all come back for recommendations from the asylum or to the asylum as maybe, I know people in the asylum. I can get you into the good asylums. And then you can get me. This is the deal. I write recommendations to get you guys into the good luxury asylums with like the swimming pools and the squash courts. And then you write recommendations that can put me in the expensive nursing home. Okay, that's our deal. Grippy socks. Oh my God. Okay, that's it. I'm just I can't believe you guys aren't taking this would all be fine if I was going to see you all in 204. I'm just not going to fail you all so I can see you again for another semester. I think that's fair. Sounds like a good deal to me. Okay, grippy socks. It's all about the grippy socks. Yes. Okay. Luckily, everything that's written on the board is what I just explained 5 minutes ago. So I'm going to move on in a second. But yeah, but it is a takeaway. And it's like important for the very last thing that we're going to say on Monday. Honestly, the reason I keep harping on this normal force business, it's not actually meant to be it's not meant to be irrelevant. Then I want to keep harping in that two things. One, yeah, the normal force doesn't do any work. Any force that's perpendicular to a displacement doesn't do any work. And yes, part of that is to keep straight. Like you got to know what angle we're talking about at any given moment. And at any given moment, part of all this inclined plane stuff too is to reinforce it doesn't matter whether you do F cosine theta times X or you do F X cosine theta, or you just do something in your head to make sure that you're just looking at the correct F component and the correct X. The key point is not to get distracted by any other theta in the problem and just always know that you're only, when you calculate work, you're only looking at the angle between the force and displacement vectors. But now here's the real thing. Well, okay, so I think you get that the work done by the normal force is zero. But the reason we keep making a thing about that is because the normal force is doing something very important. It is. And the thing that it's doing is kind of the emphasis of the very last class, like next Monday, like no joke. Oh, okay. So I need you to know that. So here it is. Here, okay. What I'm saying is the component always, this is a truism, what's on this board. The component of force that's parallel to displacement always does work, right? Like that's our emphasis right now. Whatever force is acting parallel to a displacement does do work and therefore does transfer energy, right? Transfers kinetic energy and therefore changes speed. If you're walking down some path and I start pushing you at some angle, the component of my push that is aligned with your walk, with your path, the component of my force that's aligned with what you're doing is going to do work on you, transfer energy to you, and speed you up if I'm like pushing from behind, or slow you down if I'm like pushing from in front. So that's what parallel displacements do. However, perpendicular displacements do something very important as well, just something very different. The component of force that's perpendicular to displacement, for example, in this case, the normal force, it doesn't change speed, but it does change direction. And that's a big, and it does so in a quantitatively analyzable way. Like there's math for that. Let me back up for a second and remind you, like F net equals ma, right? What's the effect of forces in general? In general, forces accelerate objects, right? And to accelerate is to change velocity, right? This is like a whole big review package in like 2 sentences here. Forces accelerate. Acceleration means change in velocity. Velocity means speed and direction, right? Velocity is a vector. Velocity is a package of 2 pieces of information, speed and direction. So forces change velocity, for sure, no matter what like way they're pointing. Forces change velocity. But what we're arguing now, what really we're doing with this whole unit is we're sort of breaking up the idea of velocity into 2 ideas in our head. The speed aspect, magnitude, and the direction aspect. And what I'm saying right here, right now, is whenever you push something or pull something, the component of your force that's parallel to the displacement will alter the speed at which that object's going, but the component of your push or pull that is perpendicular to the displacement will not alter the speed. It won't transfer energy, but it will alter direction. The way to curve something, the way to turn something is to push or pull it along an axis perpendicular to the object's motion. Okay, and I'll get it to the math. So the purpose of our very last class on Monday is to analyze the mathematical details of that fact, that statement. so the reason that we keep coming back to what's the normal force doing? Oh, it's doing nothing. It's not doing nothing. It's doing no work. It's not transferring energy. What it's doing is altering direction. And by that, I mean, if there were no normal force, if there's no plane, the thing would just go straight down, right? It's because of the normal force that that boulder is not going straight down or straight up, that it's going at an angle. Okay, I'm going to keep going now. So that's that. I'm scared to look in the chat. Okay, no. Okay.
Wait, I'm sorry. Could you go back for a
Oh
second?
yeah, absolutely. Was that Michelle F? Yes. Oh, well,
Yeah, I just had a question. At the bottom where it says velocity, what does it say in the corner?
Oh, sorry. No, really good point. The asylum is working. I can see. Yeah, it says in the corner. It says no. That is really. It illegibly says in the corner. Forces change velocity. So I'm just trying to say, like it's like a sidebar, but it's not. I'm just trying to remind you that all what we're analyzing here. So it says yeah. So to answer your question, it says forces change velocity, and the reason I wrote that is just like as a reminder that every one of these forces in every one of these free body diagrams is doing something. So and they all have to be accelerating in some way because F net equals ma. So any one of these forces that isn't, so they're all changing velocity in some way, but the forces that aren't changing speed are therefore changing direction. But yeah, it says forces change velocity. Good.
Thank you.
Thank you. Awesome. Thank you. All right. All right. So now we're on part D. And it says Sisyphus pushes up with, I don't remember what the question, oh yeah, it says Sisyphus pushes up with 700 newtons. So how much work does Sisyphus do? Okay, so again, this is like, it's really the work equals the force vector dotted with the displacement vector. But what that means is the force magnitude times the displacement magnitude times the cosine of the angle between them. And notice now, I just started out of nowhere. I'm just starting to, instead of use theta, I'm starting to use phi, just to emphasize, like, it's not any random theta. It's not the theta that's given in the problem. It's not 33 degrees, right? It's the angle between the force and the displacement. And in this case, if you're talking about Sisyphus, unlike gravity, Sisyphus actually is pushing along the lines of the displacement. So the angle between the force and the displacement done by Sisyphus is 0. So the cosine is 1. So there's like no extra. So everything Sisyphus is doing is efficiently going right into the energy transfer. So he's doing positive 1.4. That's not strict scientific notation. I'm going to purgatory for that extra digit. He's doing a positive 1.41 times 10 to the 4th joules of work. It's positive because he's pushing up and the ball apparently is going up. Okay, so then it asks in part E, what's the net work? CBS. No, what's the net work done on the boulder? That means, okay, add up all of the works being done on the boulder. And there's 3, like this is now getting into, there's like complexity here. Well, there's like a lot of details here. There's 3 different forces doing work on the boulder. I'm adding them all up, but 2 of them are negative. Friction's going against the motion. Gravity's going against the motion, but Sisyphus is going with the motion. So I just add them all up. They're all in joules. Whatever. Okay. And so I get that crazy number, that divine number. Okay. And then now it asks, okay, assuming the thing starts from rest, how fast is it going the moment it gets to the top of the plane? So I'm doing the work kinetic energy theorem. And I'm saying that the net work done is the total transfer of or change in energy. And it's always a comparison, right? It's always that if I do 7 joules of work on you, then I give you 7 joules of energy. Like, how much energy do you have? I don't know. It depends on how much you started with. All I know is I just gave you 7 more, right? So, but in this case, it says we started with 0. So I solve for V and I get 8.92 or approximately meters per second at the top. So that's that. So we go on. So then we go to this piano mover. Now this is like a little interlude problem. I mean, it's like sort of stuck in there. It's taking us away from gravity for a minute. The reason for this little interlude problem, I believe, is they just want to again make sure that we haven't gotten this whole idea of angles all confused in our mind, or I don't actually know why it's here. But oh no, I do know. Yeah. Okay, right. They want to make sure that we're not just like now just memorizing results rather than understanding the fundamentals of work. So we go back to this piano situation is much like this child sled situation. We got this piano, it's going across the floor or across a horizontal floor. We're pushing it, but we're pushing it at an angle as measured from the horizontal. And it's going in the direction we're pushing it. Nothing else is going on. There's no friction or anything. So it asks for the work that we're doing as we push this piano through a displacement of 20 meters. And yes, again, like no matter how you slice it, you can say that the work is F magnitude times X magnitude times the cosine of the angle between them. Or identically, you could just say, oh, it's the component of the force. Like you could think of it as Fx cosine theta, or you could think of it as F cosine theta times X. It comes to the same thing. We're just saying, you get it, I think. So we get like 7.73 times 10 to the third joules. And then it asks, yeah, see, this is why, okay, here's why they just stuck this problem in here. They ask the work done by gravity, and they just want to make sure that you've gotten the concept and you're not memorizing things like the work done by gravity. Even if you want to memorize that the work done by gravity is always mgh, you can even, like, actually, that is still true. The work done by gravity is always mgh, but h means height change. It means vertical displacement, right? We're saying that the only work that gravity ever does is to get something from one height to another, because gravity is always along the vertical axis, so it only cares about the vertical component of displacement. So even if you're just like blindly memorizing and saying work done by gravity equals mgh, the h in this case is 0. Because the box did not change. I mean, the piano did not change its height at all, right? I don't know what height it started at, but I know it ended at the same height. So it's 0. So that's one way to think of it. Or realize that in this case, what gravity's doing here, if you drew a free body diagram, what gravity's doing here is precisely what the normal force was doing in the other problem. Gravity is pulling, it is exerting a force. The box is displacing, but the angle between the force and the displacement is 0. So gravity is doing no work. It's not doing no thing, but it is doing no work, i.e. gravity is not transferring energy to the piano, i.e. the piano is not getting faster or slower in any way as a consequence of gravity. So the answer is 0. Okay. That's that. So then we get to this sort of dizzy looking roller coaster thing, field trip, in our minds. How hilarious would that be if like a class that couldn't even meet in person somehow managed to do a field trip? Like, maybe we could do a Zoom field trip. Oh, maybe that's what we did yesterday. Yes. Wow. Yeah, I shouldn't have gone there, but he went. Yes, right. Field trip to the asylum. I kind of feel like that's what every session of this class is actually. Okay.
It's not a field. We all just happened to meet there.
Oh my God.
Michelle, you're on fire today.
I do have to agree. I mean, see what it's doing for class morale. It's just like everybody now. Melita's like all like everybody. It's just like it's a part. I mean, yes, and if we even learned physics too, then it would be a total success. I mean, I mean, thank goodness that the only requirement, apparently, according to this class, this syllabus, our spiritual syllabus, apparently the only requirement for heaven is scientific notation. And that's a darn good protection for me, because clearly if it weren't for that, I would be going to the other place, like on the express train, for allowing all this. But yeah, no, not even just for allowing it, for the fact that I'm enjoying it so much. That's really what the problem is. Okay, but my God, it is so the end of the semester. Okay. Yeah. Yes, I'm feeling very bonded. Well, that's what grippy socks do. They bond. I mean, yeah. Actually, watch this segue. You know what grippy socks really do, folks, in the asylum? Well, I shouldn't even make jokes about this. I mean, anyway, and if you, yeah, okay. By asylum, I think we all understand we mean my house, right? Okay. But you know what grippy socks do? Watch this. This is 30 years of teaching experience about to amortize right now. What grippy socks do, ladies and gentlemen, is they increase the coefficient of kinetic friction. Which brings me back to, okay, yeah. Okay, I have to stop looking at the chat. The chat is evil. How many ADHD professors does it take to screw in a light bulb? Look, a fish. Okay, roller coaster. All right, so for the roller coaster, big picture. Yeah, yes, we are. All right, all right. Why do I keep looking at the chat? Can we get the sponge room? You can't say that. Oh my God. Wait, spiritually connected? See, yes, you can say spiritually connected by grippy socks, but you can't mention the sponge room. You can't know about that. Lord. All right, all right. I hope you're looking at the diagram because it's a complicated diagram. The work done. Stop it. Stop it. Do you ever wonder how I got through school as a student? Yes, don't. Because it was different then. We didn't have diagnoses, we just had consequences. Okay. I gotta stop. Wow, this is really all right. Hey, well, one thing I'm gonna work. I didn't visit. Like, what are you kidding me? Like, I was like a permanent resident. Yeah, seriously. I mean, come on. Okay. We can do this. I am going to warn you, since I do seem to be falling apart here, that not going to warn you. I'm going to remind you that if by some strange twist of events, I don't get to the final answer of all this, which I really should, but if somehow the clock runs out in 18 minutes, please do remember that all the answers are in this PDF, which will be uploaded. Oh, thank you. See now, okay, I can take that. Thank you. I mean, collapse all. Actually, I don't even know what to stop. Okay, I'm putting the chat. I'm like hooking up another monitor to my computer so that I can move the chat over to that monitor. Thank you. Thank you. Stop. Seriously. Oh my God. Wait, I think I have to walk away. Has this ever happened to me before? Yeah, probably, but not in recent. Hang on.
I'm in charge of class now.
Oh my God, I'm coming back. Wait, stop. Oh, you probably do a better job, actually. All right, no, really, I do appreciate this.
I'm sorry. I'm sorry. I broke him, guys.
Yeah, I think you broke. Yeah. Oh my God, that is such an expression of your generation, and it is so apt. Yes, I do think you broke in a good way, but not in a way that's necessarily going to help your knowledge of physics. Right. Okay. Wow, Chris, stop. No, Michelle. Okay, wait. All right, wait. Okay, I'm over here. I don't know if you can see it. I'm over here. I'm going to just read off this over here. I'm like, yeah, I'm literally turning away from the chat and I'm just looking at this physics here. Okay. You want to know what's really, no, you don't. But part of the problem is, besides the fact that you are so funny and it is entertaining and it is putting me in a better mood than like, I hate this part of the year as much as you do almost. But the other problem is now we're in this weird zone. If you really want to know how crazy the craziness is, now we're in a zone where I'm like afraid that someone will make a joke, that someone who hasn't ever spoken yet in the semester, that someone will finally feel so comfortable and so safe now in the last week that someone will like eke out some like nice, well-meaning joke to like be part of everything and like show solidarity. And like, I would feel so happy for that person if they did that. But I'm afraid they're going to like make some joke or something. And I'm not going to see it because I'm trying to go back to physics. And then I don't respond to it. And then they're like, oh, great. Mine was the one non-funny joke. Like, that's what happens when I try to participate. I knew it. Everybody hates me. Yarobaum hates me. I suck at physics. And then like, right? And then the rest of their life is like trauma response because I didn't look at the chat for like that 1 second that they finally came out of their. That's literally what's going through my mind right now, just so you know how dark a place it is in here. Okay, like I don't even care if nobody learns physics at this point. I'm worried that one person who might have actually achieved like a sense of serenity in the world is now going to be deprived of it because I chose that 1 minute to teach physics rather than care about humanity. Do you see how hard it is? You see how hard it is? Okay, wait. Well, that's my that's my
It's completely broken.
villain story thing is, oh my God, I am completely not it's I don't think my darkness is evil. I think it's a little misguided. They're not, more empty than evil. No, it's not empty, it's freaking crowded. Are you kidding me? Okay, so seriously, so take this for here in the 14 minutes that we have left and I try to do physics. If you are that person that finally feels comfortable in a science class or whatever, which again, by the way, who are we kidding? This science class is meant to be like the healing for all the damage that we all experienced in every prior math and science class, like for real. So if you're just getting healed now and you're about to finally feel okay in the world of academic science and math, please accept my advance apology. Your joke is funny and I will notice it at the end, or your contribution to physics is accurate and I'll notice it at the end, but it's not personal. If I don't see you now, I'm going back to the board. Oh my gosh. Wait, I wonder if he knows. See, I can't Perry. Wait, what? Okay, no, see, what? Why am I doing? Why? See, I'm looking. All right, I'm good. But thank you, Melita. Yeah, see, that's what I want to see. And man, oh my God. Well, I know, but oh my God. Okay, okay, I'm too. Oh my God. Oh my God. Okay. No, you guys are awesome. I can't believe you're all leaving me. Now you have to develop an abandonment you have to inherit my abandonment complex. Okay, the roller coaster. This is where I'm not looking. I'm sure it's hilarious. Okay, the work done by gravity from A to B is negative mgh because the thing is going up, but gravity is pulling down. So it's negative mgh. It's 800 times 10 times 38. It's negative 3.04 times 10 to the 5th joules. Then part B says, what's the work done by the normal force? Well, duh, it's 0 joules. If we've learned nothing today, I'll go on. C, what's the kinetic energy at point A? It's 0 joules just because that's actually kind of weird, but the problem says that the cart starts at speed 0, like at the bottom of this roller coaster thing. And like, it wouldn't go anywhere. Nothing would happen except it happens to be like, there's an engine that's driving the car. So, so the answer to C is 0 joules, not OJ Simpson. Then D, what's the kinetic energy at B? Well, that's straight up. It tells you that the speed it achieves at point B, it tells you that the speed is 2 meters per second. So, and you already know the mass. So that's a plug and chug. Kinetic energy is 1 FmV squared, 1600, 1.60 times 10 to the 3rd joules. Okay. Then E, it asks what's the net work done on the car from the point A to point B. All of these are, once you, like everything in physics looks like a plug-in once you know what you're doing, but, of course, but this one, so it looks like a plug-in maybe, but this one's like a little bit interesting, only in that now we're going backwards in the reasoning, right? It's asking you for the net work done from A to B. And you might think, well, okay, so I've got to add up the work done by gravity with the work done by the engine or something like that, but I don't know the force exerted by the engine. Or you might think something like that, but it actually wants you to go backwards. it wants you to say, since you know how much the kinetic energy changed, you know how much kinetic energy this car just gained, then you must be able to infer how much work on net was done on it, right? So we're going backwards. We're getting that the net work is the change in kinetic energy. It's 1.60 times 10 to the third joules, okay? Only again, because of the assumption that the thing started from rest. So then it asks, what's the work done by the engine? And that sounds like an outrageous, like, how the heck do I know what the work done by, when did we learn about engines in physics? But it's just saying, if you go to the next page, I don't directly know anything about engines, neither does Tesla, but I know how to charge a lot for like electronics. But I know the network, the total work done, and I know that the total work done is the work done by the engine plus the work done by gravity. I really should say like plus, plus, but the gravity is a negative. Like, I don't know how you want to phrase that, but right, the network is the sum of all of the works. So if I'm solving for the engine, I can just subtract from both sides. I'm being a little funny with the plus and minus side, but I'll stand. Yeah, I mean, really, it's correct. I don't know. I'm being a little funny about the sides, but the point is that the work done by gravity is a negative number. So I added it to the net. So what I'm saying in the end of the day is the work that the engine has to do, it has to first of all match whatever work gravity is doing. It has to meet gravity, but then it has to do more than that so that the thing actually displaces up, right? So it has to be a bigger number than both of those put together. So it's 3.06 times 10 to the 5th joules is the work that the engine does. Then G, I believe G asked, what's the work done by gravity? But why didn't we already do that? Wait, G. Oh, so now it wants to know the work done by gravity as the car descends from the top to the bottom. So this is sort of interesting because what it's getting at now is, even though we've never been asked this question yet in the problem, we do have the information already. In other words, we know the work that gravity did to get from point A to point B, from a zero height to a height of point B. Now it's asking what work will gravity do to bring the thing back from B to D. Now, B and D D and A are two totally different places, right? And the route that this car is going to take to get back from B to D is a totally different route from, like, it's going in this windy, like, long path thing, whereas from A to B, it practically just went directly. So it's like a totally different distance. It's a totally different path, and it's in the opposite direction. But we're so confident now that gravity only ever cares about vertical displacement. The work to get from one height to another is negative mgh if you're going up, and it's positive mgh if you're going down. All gravity cares about is the comparison between two heights. So we can confidently say that whatever negative work gravity did to get us from A to B must be the same as the positive work it does to get us back to the same height of D. In other words, what you might want to write, no joke, what you might want to write down in your notes is the work done by gravity is always path independent. It's independent of path. It doesn't matter how you get from one place to another. All that matters is the heights of those two places. So I don't have to, so I can just take my answer from part A and just plop it in as my answer for part G. The work done by gravity I just lost the number. The work done by gravity, right, is 3.04. Yeah, I got erased. It's 3.04 positive 3.04 times 10 to the 5th joules. Okay, so work is mgh is mgh. Again, with 6 minutes left, note that the work done by gravity is path independent. And in fact, as long as I'm pausing to say this, what really will be helpful for you to know for next semester is that any force that does path independent work is known as a conservative force. I mean, just write that down. Just write it down. Work done by a path independent force. I'm sorry, a force that does path independent work is a conservative force. I'll just leave it at that for the moment, but okay. So then it asks, so that was G. So then it asks H, what's the work done by the normal force from the track as the car descends from B to D? Okay, again, that's 0. Then I, what's the final kinetic energy and the final velocity of the car when it reaches point D? Okay, this is a little bit involved, not really. The idea here is like this almost, this is now looking like a complicated question, perhaps comparatively. But the whole idea here is we've been told that the engine is turned off, and we've been told that the car came to a full stop at point B, right? So now the car is just gliding down from point B to point D. It's doing it in a funny way. It's going over these bumps and these valleys, but the only force doing work on the car is gravity as it goes from B to D. So, so the net work done on the car is mgh, and that means mgh is entirely responsible for any change in kinetic energy, any transfer of kinetic energy to this cart. And the cart starts at point B with no kinetic energy. So this is so as complicated as the picture looks, and as many details as we've been navigating, the real lesson here is if this thing falls from B to D, to figure out how fast it's going when it gets to point D, it's literally the same calculation we could do if it just fell straight. If it literally fell, well, first of all, it's the same calculation as if it fell from B to A. But even more to the point, it's the exact same calculation as if we just dropped something from B and let it fall to the floor straight. Like that's how, if we just ask how fast would it be going when it hit the ground, it literally is the same speed as if we just dropped it, which is, I think, sort of surprising. It's sort of interesting. So it's just mgh equals 1 FmV squared, so to speak. And so the kinetic energy, so the 1 FmV squared at the bottom is mgh, 810 times 38, 3.04 times 10 to the 5th joules. And therefore, if you want to get the speed at the bottom, you say that kinetic energy equals 1 FmV squared, and you plug in for m and you solve for v, and you get approximately 27.6 meters per second. Oh, and we have one more to do and 3 more minutes. How is this happening? So we get 27.6 meters per second. Sorry. He's almost right, but not quite. Okay, part J, the very last part with 3 minutes to go. I'm going to do this, guys. I'm going to prove something. So it asks when the car reaches point C, it's going 20.5 meters per second. Find the elevation of point C above ground level. Okay, that sounds like a complicated question. That's as complicated as it gets for this problem, but the key point again is what I just said, that really all that's happening here is a trade-off of mgh and 1 FmV squared. It's falling from point C to, it's falling from point B to point C. And this is exactly what I said at the beginning of before all the mayhem of the class. Like, this is a classic example of, the speed at some spot, you're trying to find the speed at another spot, or more to the point here, the speed at one spot, you're given a different speed, you're asked to find the other spot. It's a speed spot correspondence. So it's totally a work energy thing. It's totally an mgh 1 FmV squared correspondence. The thing goes from one height to another. Well, you see what I'm writing here. Like the difference in mgh, the work done by gravity as it goes from one height to another equals the gain in kinetic energy from one height to the other. And I chose as my 2 points of comparison. This is sort of important. We have 1 more minute. I chose as my 2 points of comparison C and D. Like I'm comparing C to D. So my height at D is 0. But I know the speed at C. But okay, so you see what I'm doing here. So I plugged in the 2 V's that I know and I solved for H. I mean that, and I got 3.42 times 10 to the second meters, and class is over. So there. Okay, so but yes, have a good. No, I'm not. Okay, so but we're done. So I don't know what that proves, but have a great lab. I will miss you terribly, but then I will see. Yes, have a great day. I will see you on Monday. Yes. Oh. Okay, and I'm turning off. Yes, have a great day. Have a great day. Yes, you guys are amazing.
Sorry for the utter distraction today.
That was totally awesome. I'm going to turn off the recording, but no, that was great.